Go. All right, assume all variables are differentiable functions of time. So number one, says the volume of a cone has the equation, volume equals 1/3 pi r squared h. We're going to write an equation that relates dv dt to dh dt if r is held constant. All right, that's a lot, huh? So what we're going to do is we're going to take the derivative of the volume with respect to time instead of the radius or the height like we've been doing. Okay? So here we go. Let me show you what we're going to do. And r is held constant. So you have to think of r is just, a constant. It's not a variable. H is going to be our variable, though. Okay? So here we go. So the derivative, there we go. dv, that's nice. I like that. dv dt is equal to, dv dt equals, okay? So we're going to take the derivative of this. H is our variable, okay? So the derivative of h is just 1, right? So we have 1/3 pi r squared. And now we're taking the derivative of h with respect to t, so it's going to be dh dt. Remember when we did implicit differentiation and we took the derivative of y and it's dy dx? Then when you take the derivative of x, it's dx dx. Remember when we did that? Like when you have y squared equals 3x and you have to take the derivative of that. Do you remember doing the derivative of y squared is 2y what? Times y prime, dy dx. So that's what I'm doing here, because now I'm taking the derivative with respect to time, t. So when I do that, I have to do derivative of volume with respect to time, and then derivative of h with respect to time is dh dt. And that's your answer. This whole thing's not a constant, though. This right here, this 1/3 pi r squared, that's the constant times h to the power of 1. Exactly. Yep. No, I'm glad you said that. No, that's right. Okay, letter B. Now we're going to write an equation that relates dv dt to dr dt. So now we're going to take the derivative, and h is going to be held constant this time. Okay? R is not. So let's do it. Bless you. So you get dv dt equals, so I'm going to take the derivative of r squared. So what do? You bring the 2 down front. So you get 2/3 pi r h dr dt. Okay? H is a constant now. So you could think of this as it was 1/3 pi h times r squared. So you're bringing the 2 down front, subtracting 1 off, but then you have to put that dr dt, because it's not the derivative of r with respect to r, or the derivative of volume with respect to r, it's dr dt now.
Real quick to the first one.
Yeah.
What would you put?
Okay, so why is it that we have like we take the derivative of r first on that one? I mean,
R is held constant,
okay.
and then they switched it.
Okay.
Now H is held constant.
How come there's
Why is there an H
but
still?
there's not an H in
Yeah, that's what I'm trying to say.
Because we took the derivative of H, which is 1.
H is not squared, but R is squared, so R stays in because it's
Exactly. Yep. Yes?
when you take the derivative of something with the first power.
Mm-hmm.
Okay, and then
Yeah?
what would we plug in for like you did this?
Oh, we're not quite there yet. So we're just practicing derivatives of certain things. No?
It just doesn't really make sense.
Okay.
Whatever anyone just said confused me. I had it and I'm confused.
Now you're confused? All right. So let's do this.
Like the D over something, that's just confusing.
If we had volume of a cylinder, volume equals pi r squared. Okay? And let's say that we're going to take the derivative of this, and we're going to say that r is constant, and h is our only variable. Okay? That means this whole thing is a constant. Think of it as 10 or 5 or whatever. So I'm taking the derivative of h, but I'm not doing dv dh. Okay? This is not y and x. Well, it is y and x, but I'm not taking the derivative with respect to x or h. I'm doing it with respect to time, t. So when I take the derivative of v, I have dv dt When I take the derivative of h, you bring the 1 down, pi r squared. H is gone, right? 1 minus 1 is 0. And then times dh dt, because it's the derivative. Okay, so then the other one, are we good with the other one too?
Yeah.
Because Peyton explained it really well. You bring the 2 down.
Explained that part and
That made sense. Okay.
Made that make sense, basically.
Okay. So we're ready?
Yeah.
Now the next one, you might like the next one better, even though it's harder than the other two. We are now going to take the derivative of volume with respect to t, and nothing is going to be a constant. They're both variables. Okay? So when they're both variables, you're going to have to do product rule here. So let's rewrite this. So the volume equals 1/3 pi r squared times h. But let's group 1/3 pi r squared and h separately. Okay? Now nothing is a constant, well, except for the 1/3 and pi. But the r squared and the h, those aren't constants this time. They're variables. So we have to do product rule. Okay? So we're going to take the derivative of this whole thing with respect to t. So we're going to go dv dt equals a times b prime. So a is this whole part right here, this 1/3 pi r squared, times the derivative of h with respect to t, which would be what? 1 dh dt. Okay. dh dt plus, that's ab prime plus b, which is h, times a prime. So now we're taking the derivative of 1/3 pi r squared with respect to time. So that would be 2/3 pi r dr dt. Yeah, and that's it. And you can, fix that, clean it up, whatever, but that's pretty much it.
So since it's a respect to...
Yes, that's the hard part, the respect to t.
You have to always multiply it by...
Yep, exactly. Okay, so now, here we go. Let's put this into an actual problem. Yes, they're all word problems. But remember that one chapter that we did all word problems and you loved it?
Yeah, that was a chapter.
Yeah, but this is
This is too hard?
another.
Okay, it says, suppose at noon the radius is 10 inches and the height is 60 inches. All right, so I'm going to write that down. The radius is 10 and the height is 60. Now, at this time, the radius is increasing at a rate of 2 inches per minute. Okay, do you know what that is? That is dr dt. Remember, derivative is a rate. It's a rate of change. In this case, we have the change in the radius over the time because it's changing at 2 inches per minute. So dr dt is 2. You can write inches per minute if you want to. It's a rate. All right, then it says the height is decreasing. Ooh, this looks like some fancy cool thing. What's going on here? The height is decreasing at a rate of -3 inches per minute. -3.
Are we doing exactly the same thing, just plugging these numbers?
Yes. All right. Is the volume increasing or decreasing? What is the rate of change of the volume at noon? So we already found the change in volume. We can just plug all this information into here. It's right here, right? Remember, we kind of did these before. Remember husbandry and the bushels and the apples? You remember that one? No?
No.
Okay. Never mind. Never mind. No, nope, never mind. All right, so here we go. dv dt equals. dv dt equals. And we're going to plug all this information in. So we have 1/3 pi. R squared would be 100. 10 squared. Let's just write it out. 10 squared. And then times dh dt. Do you see that? And we know that dh dt is the change in the height per time. Change in time would give us -3 plus the height, which is 60, times 2/3 pi times r, which is 10, times dr dt, which is 2. All right. And then you get your calculator out. Beep, boop, and you get 700 pi cubic inches. It's increasing, that's positive. 2,199.1 cubic inches per minute. Because it's dV dt, it's the change in volume over time. So that's what it's increasing by.
How did you get 2,199?
Plugged it all in.
You just multiplied by pi, right? You just 700 multiplied
Oh, by pi. Yep. 700 times
So
pi.
since it's positive, that means it's increasing?
Yep.
So if it were negative,
Yeah. So this would be increasing at that rate of change. All right, what was the volume at noon? The volume at noon, if you go back to volume, is 1/3 pi r squared h. Pi times 10 squared times 60. So the volume was 2,000 pi cubic inches.
how do you know that's at noon?
Because it started, suppose at noon, the radius is, yeah. Okay, what's the volume at 12:01? 12:01. Well,
You just add it to the
yeah, you can find it.
4,199?
Yeah, well, here's what you do. So at noon means 1 minute has gone by. And it says here that the radius increases 2 inches per minute, and the height decreases. So let's do this.
Didn't you already find that it increases by?
Yes, so I'm kind of comparing. Like this is the estimated, and this is the actual.
Oh, okay.
And then we're going to see kind of how close they are. So volume would be 1/3 pi. What's r at 12:01? 12. Because it increased by 2. So times, I kind of run out of room there. 12 squared, and then what's the height? 57. The height was 60 at noon. At 12:01, it decreased by 3 inches, so it's 57. And so you get that the volume is 2,736 pi cubic inches. Look what it increased by. 2,000 to 2,700. It increased by 736 pi cubic inches, and we got about 700. We got 700 pi when we did it.
Would you have taken 2,700 pi?
Yeah,
Like as an answer?
yeah. So when you're doing this estimated thing here, it tells you that it's 700 pi cubic inches is what it's changing at. Yeah, 2,700. It's really
Like,
close.
We wouldn't have to like go through.
Well, yeah, if I might ask you to, you know,
Find the exact
yeah, find the exact. Okay, now let's look at a very interesting problem on the next page.
That is very interesting.
It is very interesting. All right, so
I'm not looking forward to this.
no,
What is this quiz?
We don't have a quiz on this. It's a project.
you have a project.
Oh, thank
Oh,
goodness.
It's
Yeah,
not.
I can't even pay attention when you play.
dude,
Okay.
watch your video. Her videos are the best.
Whose?
Yours.
They are? I thought they were trash.
See,
That's
he
so
thinks
nice.
it's more-
Thank
He
you.
thinks it's more practical to
watch the
it.
videos when he can't ask questions, then.
Oh, okay. All right.
No,
Okay.
because I could skip the like useless parts.
What? What's useless? Like this part right here where I'm talking to you? Okay. Here we go. All right. It says here. A particle. I love those. Particles moving along a curve, xy equals 12 in quadrant 1 as shown in the plane. Here it is. The coordinates x and y are differentiable functions of time. The particle's moving southeast along the curve. See, this is from my dad. I use it still. And it's moving this way. He even wrote arrows in there, which is really nice. The particle's moving southeast along the curve. The distance d from the origin is given by d equals the square root of x squared plus y squared. As the particle moves, the distance is changing with respect to time from the origin. Southerly, it's moving in a y direction. Easterly, it's moving in an x direction, dx dt.
I've never heard southerly.
Southerly?
I've never heard that.
Southerly. Okay, it says write the expression that expresses the southerly rate dy dt. So we have xy, oh, I need a color again. We have xy equals 12. Okay, most of the time, you write this as y equals. So this is y equals 12 over x. It's a nice little rational function. You did a lot of those in RAM and ham. But we're going to go ahead and find the derivative of y with respect to t. Okay? So this would be y equals 12 times x to the negative 1, if you want to rewrite it like that. And now let's take the derivative with respect to time. So the derivative of y would be what? dy dt equals negative 12 over x squared. You get negative 2, bring it down. And then times what? dx dt. Very good. Okay? So that's a negative 12. Negative 12 over x squared times dx dt. So we're going to hang on to that for a minute.
Why is it
DX,
DT?
Okay, so this goes back to the whole implicit differentiation thing. So if I have y equals, say I have y equals 12 over x, and I want to take the derivative of this. Usually it's the derivative with respect to x. That's what we've been doing the whole time. So derivative of y is y prime or dy dx. The derivative of this would be negative 12 over x squared. And we don't ever write this, but it's the derivative of x for x, dx dx, which is just 1. But you're not going to do that every single time. So now I've changed the variable on you. I'm not telling you to take dy dx. I'm asking you to find dy dt. So it's different. So when you find the derivative of dy dt, you take the derivative of y, which is dy dt. You take the derivative of x, so you have negative 12 over x squared, but it's not dx dx. It's dx dt with respect to t instead of
So we just
x.
haven't been writing the DX.
We haven't, no. We did that, remember when we did implicit differentiation, you had to go 2y dy dx, remember, like every single time? That's what it has to do with. All right. When the particle is at 4,3, it is moving east at 8 feet per second, FPS. So what is dx dt? Well, it just told us right here. Dx dt is a rate, okay? Dx is going to be in feet. The time is in seconds. So dx dt would be 8. 8 feet per second. That's the rate. What is the speed going south? Well, the speed going south is dy dt. Okay? So the speed going south would be dy dt, which is equal to, we're going to plug everything in, negative 12 over what? 4 squared, see this is x and y, 4, 3, x and y, 4 squared, times dx dt, which is 8. And so this is negative 6 feet per second. Wouldn't you expect that that would be negative? Look at the particle. Look at where it's going on this thing. It's going down and it's going to the east. So it's going in a positive x direction while the y's are going negative. Okay, which equation that expresses the rate of change at which the particle is moving away from the origin? Oof, this one's bad. You're gonna love this one. Here we go. All right, so here we go. From the origin is really ugly. D equals the square root of x squared plus y squared. And we have to find the change dd over dt here. Now you can do this a couple of ways. I suggest to just go ahead and square both sides so that you're not going to have to do all that, that would be a lot of chain rule there. So square both sides and get d squared equals x squared plus y squared. Okay? And this is going to be so much easier when you do it this way. Now, take the derivative of the whole thing with respect to t. Okay? So here we go. Derivative of d squared is going to be what? 2d dd dt equals, so you take the derivative of it, and you put the d dt next to it, and the next one would be 2x dx dt plus 2y dy dt. Yeah, you're getting the hang of it. Okay? So none of these, we're not taking the derivative with respect to any of these variables anymore. It's all respect to t. So it's always d whatever dt. Okay? All right. And then you could, if you wanted to, divide everything by 2. I mean, you don't have to, but you could. All right, so here we go. Now, what is the speed? Yeah?
Multiply everything by dt.
No. No. I mean, you could, but you don't want to. Yeah. All right, what is the speed at which the particle is moving away from the origin at 4, 3? Use answers to B and C. Okay, so here we go. We need to take this right here. We got to plug everything in. We're trying to find dt, right? What is the speed at which the particle is moving away from the origin? Trying to find the rate of change at dt. So here we go. We're going to plug everything in. 2 times, so what would d be? Our point is still 4, 3. So go to here and plug it in. 4 and 3, 5. It's the old 3, 4, 5 triangle, right? Haven't said that in a while to you. 2 times 5. Okay, they gave you that formula, d equals the square root of x squared plus y squared, but it just comes from the Pythagorean theorem. All right, so 2 times 5 times dt equals 2 times x. What's x? 4. Okay, what is the speed? What is dx dt? 8. This is still at that same point, 4, 3. That's at that circle that's on the map. And then plus 2 times y. What's y? 3. And then dy dt is -6. All right, so we get, I should have divided everything by 2 earlier.
Is that 2 times 4 times 8?
2 times 4 times 8. Yep. So you get 10 d dt equals, this side is 28. Divide by 10. So the particle is moving away from the origin at a rate of 2.8 feet per second. 2.8 feet per second. Don't forget, if the problem has words in it, your answer has words in it, right? Most of the time. Okay, last one for the day. All right, suppose the particle continues east at 8 feet per second until it gets to the point 6,2. At what speed is it moving away from the origin now? Ooh.
Would everything be the same except for 4 and 3?
Not quite. You'd have to go back and find some certain things. So dx dt is the same, right? It continues east at the same rate, so that's going to be 8. dy dt would be what we found from up above. Where is it?
So it'd be -12 divided by...
-12 divided by, yeah, there it is. -12 divided by x squared, 36, good, times 8. Because it was, -12 over x squared dx dt. So that would equal -8/3, kind of a gross number. -8/3 feet per second. Okay. And then let's go ahead and when we plug all this back in, we're going to use that same equation again. We need to know what d is. D is the square root of 6 squared plus 2 squared, so it's the square root of 40. You don't need to rationalize that, it's fine. Okay, so now we can plug everything in again.
Where did you get it? dy over dt?
Oh, that was from way back here, right here. dy over dt is -12 over x squared times dx dt. But now my x is changed. Okay, so let's go ahead and plug in. Here we go. We have 2 times rad 40 dd dt equals, it's going to equal 2 times x times dx dt. So 2 times 6 times dx dt is 8. 2 times 6 times 8. Plus, what is it? 2y dy dt. 2 times negative 8/3, good. Okay, so then once you do that in your calculator, you end up getting about 6.75 feet per second. So it's increasing. It's going faster away from the origin than it was at the 0.34.